First of all, we have to understand what is freezing point. So freezing point means the liquid component turns into solid form. Liquid component which turns into solid form known as freezing point. So it is specifically defined as a temperature at which vapor pressure of the liquid is equal to vapor pressure of the solid, known as freezing point. It is defined as the freezing point defined as temperature at which vapor pressure of liquid is equal to vapor pressure of solid, known as a freezing point. Temperature at which, at a fixed particular temperature, the vapor pressure of the liquid is equal to vapor pressure of the solid, known as freezing point. Understand? So what is mean of the depression? So depression of the freezing point means the freezing point decreases. Freezing point decreases. Look at one example here. If we have used a liquid component here, that is H2O. The H2O particle is there. The H2O particles, when these H2O particles are kept into a refrigerator, what will happen? The liquid turns into solid form, that is ice cube form. Why they turns into solid form? Because the liquid particles in which between them attain the hydrogen bond is present. Liquid particles between them present hydrogen bond. Right? When you keep it into refrigerator, the water particles are come close to each other at a certain distance. They attain, then liquid component turns into solid form. Right? So when we have to apply the when we kept into refrigerator, then liquid component where they are come close to each other, and they turns into, when these both particles are come close to each other, and finally they turns into solid form. So it means the liquid particle turns into solid form. Particles are come close to each other at a certain distance, and they turns into solid form. When we add some non-volatile solute, like NaCl, when we add the non-volatile solute like NaCl, then what happens? That when we add the NaCl here, then Na plus and Cl minus are completely dissociated in the solutions. Na plus and Cl minus are completely dissociated in the solutions. After dissociation, these particles are occupy space between the water particles. These particles are occupy space between the water particle. So when these solutions are again kept into refrigerator, then what will be happen? So these particles, Na plus and Cl minus particle, are obstructed the interaction of hydrogen bonding. Right? So like here there will be no obstruction here because only H2 particles are present here. So when here NaCl particles are present, so these particles are causes obstructions of the hydrogen bond. These NaCl particles, Na plus and Cl particles, are occupy space between the water particle, and these particles are causes an obstruction to the hydrogen bonding. So that's why the freezing point of the solution decreases as compared to respective solvent. Freezing point of solution decreases as compared to respective solvent. That is only we call as a depression of freezing point. That is only we called as depression of freezing point. Understand? So here, when solvent particles are freezes at particular temperature, for example, these solvent particles are freeze, then we know that, for example, H2O, which is freeze at T0, that is 0 degrees Celsius. the solvent is there, solvent is in pure form, only one type of particle present, then we consider as a T naught F. That is solvent we consider as a T naught F. And H2O particle freeze at 0 degrees Celsius. Again, when we add the non-volatile solute, that is NaCl, in this solvent, then the freezing point decreases. Means it may be -1 degree Celsius, -2, -3, -4, anything. It will happen. So we will just consider as Tf is equal to -2 degrees Celsius. We consider as a -2 degrees Celsius. Right. So it means the freezing point get decreases here. Freezing point get decreases here. Understand? Freezing point decreases. So whatever the, we will write the graph about this. So here this is 0 degrees Celsius, here the +1, +2, -1, -2, like this. So the graph which is between the vapor pressure and temperature, between the vapor pressure and temperature, right? Between the vapor pressure and temperature. Then the water particles are freeze at 0 degrees Celsius, and it will show the vapor pressures this level, and solution particle freezes at here, and it will show that in which vapor pressure here decreases here. So it will freeze at -2 degrees Celsius. Vapor pressure also decreases as compared to the solvent, so it will be considered like this. So this is we call as a T naught F. This is we called as a, this one we called as a T naught F, and this freezing point of solution we called as a TF, and the differences we consider as a delta TF. This we consider as delta TF. So change in freezing point, delta TF is equal to T naught F minus TF. T naught F minus TS. It means higher minus lower. Higher freezing point minus lower freezing point. Right. So what is the freezing point of water? That is a 0 degrees Celsius. And here this one is the -2 degrees Celsius. And the difference, that is delta TF is equal to +2 degrees Celsius. Right. So this is the freezing point. And understand, students? So let's move to the new term. I will use this one. And what a freezing point is there? The freezing point of the component. Freezing point of the component is the change in freezing point. It is change in freezing point. Change in freezing point, which is directly proportional to the molarity. Change in freezing point, which is directly proportional to molarity. If the freezing point, the change in freezing point, that is delta TF, is directly proportional to the molarity. It means the whatever changes of freezing point occurs because the change in concentration. That concentration term here used here as a molarity, number of moles of solute present in per kg of the solvent. That is molarity we are using here. And delta TF, proportional constant considered as Kf. Yeah. So delta TF is change in freezing point, M is the molarity, and what is mean by the Kf? So what is mean by Kf? Kf means when 1 mole of non-volatile solute, added to the solvent, 1 mole of non-volatile solute added to the solvent, that is water. So water freezing point changes 1.86 Kelvin. So that is considered as a Kf. That is a constant value, right? Constant value. That is Kf. For example, if I use the solvent, that is H2O, we know the T naught F, that is freezing point, that is 0 degrees Celsius. Right? In which if we add 1 mole of NaCl we add, that is 58.5 gram. 58.5 gram. So 58.5 gram of NaCl we add, then it turns into solution, that is NaCl solution. turns into NaCl solutions, right? We know the T naught F, that is 0.86. T naught F is the 0 degree Celsius. When we add 1 mole of NaCl, that is 58.5 gram of NaCl added to in this solvent, in this case the freezing point of the solution, undergoes, there is a occurs, that is 1.86 Kelvin. 1.86 Kelvin freezing point changes, right? So that is we call as a Kf. For example, we know that delta Tf is equal to T naught F minus Tf. T naught F, that is 0 degree Celsius, minus Tf, how much changes? 1.86 Kelvin. 1.86 Kelvin changes when we add 1 mole of solute. So delta Tf is minus 1.86 Kelvin, right? Understand? So when we add the 1 mole of non-water solute in this solvent, then water undergoes 1.86 Kelvin of temperature is lowered. Water undergoes 1.86 Kelvin of temperature is lowered. Understand? So that is the Kf value. The Kf value is constant, that is 1.86. Clear, students? Hello students, today we are going to discuss the topic freezing point. The freezing point, change in freezing point. Change in freezing point according to Van 't Hoff factor. According to Van 't Hoff factor, the Van 't Hoff factor state that when we add the non-volatile solute in a solvent, the solute may be dissociated, may be associated. Solute particle may be dissociated or may be associated. So that is we are considered as a I. I means it's the Van 't Hoff factor. It means the solute particles, it may be dissociated, or it may be associated. Solute particle may be dissociated or solute particle may be associated, right? Understand? So that's a matter. That's why the delta Tf Ki Tf into m, the formula has been changed. It is when we add the number of moles of solute added into the solvent, then it may be solute particle may be dissociated or may be associated. I. Freezing point. Freezing point of the component which is inversely proportional to concentration. Freezing point. The freezing point which is freezing point of the solution which is inversely proportional to concentration. So concentration means freezing point inversely proportional to what? We directly write V by N. Understand? V by N. So it means, for example, 1 by C. If you write concentration means number of moles upon volume, or we have to write here volume upon N. That is freezing point volume. It means the number of moles of particles are increases, freezing point decrease. Number of moles of particles are increased, then freezing point decrease. If volume increases, freezing point also increases. Volume increases, freezing point also increases. So it means here the freezing point is directly proportional to volume, and the freezing point which is inversely proportional to number of moles. Volume increase, freezing point of the solution increases. Number of moles are increases, freezing point decreases here. Look at one example here. One example, students. 0.1 molar NaCl and 0.01 molar NaCl. Look here. Here I choose the two different concentration of the NaCl. One is 0.1 molar NaCl, another one is the 0.01 molar NaCl. Right. So it is 0.1 molar, 0.01 molar. According to this formula, according to this formula, right? Is it? Okay. This formula. Fp freezing point is inversely proportional to constant number of moles. Freezing point directly proportional to volume. That is only I wrote here, right? So 0.1 molar NaCl, 0.01 molar NaCl. Both are there. Both are different concentration, right? But component is same. That is NaCl. So in this case, here 0.1 molar means here the high concentrated solution. 0.01 molar means it is a low concentrated solution. Right, low concentrated solution. So it means the when we compare the concentration, 0.1 molar NaCl is more concentrated than 0.01 molar NaCl. According to this formula, number of moles are here high, then fission point decreases. So that's why the here number of moles are high NaCl. If you compare the freezing point, when you compare the freezing point, then what will be happen? The 0.01 molar, which is more aqueous. More aqueous means more volume. More volume is present, less number of salt particles are present. So 0.001 molar NaCl have a higher freezing point than 0.1 molar NaCl. When we compare the concentration, 0.1 molar is high concentrated than 0.01 molar. When we compare the freezing point, 0.01 molar NaCl, which is higher freezing point than 0.1 molar. Understand? So here, so volume increases, freezing point increases. Volume increases, freezing point increases. Concentration increases, freezing point decreases. Understand, students? Right. So it means 0.01 molar NaCl is the high freezing point than 0.1 molar. One more example. So what happened? What happened if we use different number of solute particle. What happened if we use the different number of the solute particles? For example, 0.1 molar KNO3 and 0.01 molar BaCl2, and third one 0.2 molar AlCl3. Look at here, students. 0.1 molar KNO3, 0.01 molar BaCl2 and 0.2 molar AlCl3. Right. So what will be happened here? So which one is the higher freezing point? How to arrange increasing order of the freezing point, right? So look at here. So in this case, first we have to know that the freezing point is inversely proportional to concentration. We know that, right? And one more thing, the freezing point is inversely proportional to number of particles associated or dissociated. So it means already we know that this one. We have to discuss this. So if the more number of solute particles are present, I means more number of particles dissociated. If more number of particles dissociated means the freezing point gets decreases. Understand? But collectively, if you write the formula, freezing point, which is inversely proportional to C into I. So let's see solve about based on this. We have to solve this example. First one, 0.1 molar KNO3. So here 0.1 molar C into I, concentration is 0.1, and how many? Potassium nitrate. 2 elements are present, particle dissociative form, 2 elements. Right. So the answer is 0.2, and the second one 0.01 molar BaCl2. So BaCl2, 3 particles, that is C into I, that is concentration 0.01, into 3 particle, so that is 0.03. Finally this one, third one, 0.2 molar AlCl3. So C into I, that is concentration 0.2 into particle, how many particles is 4, that is 0.8. So tell me student, 0.2, 0.03 and 0.8, during in which one have a high concentrated? The high concentrated solution have a lower the freezing point. Low concentrated even which having the low concentrated having the higher the freezing point. So we will arrange in the increasing order of the freezing point. Increasing order of freezing point T is 0.8, 0.2, then 0.03. So it means BaCl2 which having the higher freezing point. BaCl2 have a higher freezing point because the low concentrated. If it is low concentrated, it means freezing point should be high. 0.8, that is AlCl3. AlCl3 have a 0.8, that is AlCl3 have a 0.8 molar. It means the high concentrated, that is the high concentrated solution which is lower the freezing point. Understand? Thank you.